Okay, hello everyone. Hope you enjoy your coffee break. I'm Cristobal Ortega. I'm a CPU architect at ABUMPIMP. I will presenting to you today the next generation on the product of ABUMPIMP. We are developing a new PIM processor, especially for AI applications, and we will see first the main architecture of the hardware that we are developing. So first, as my colleague Sylvain described earlier, we have our existing product based on PIM DDR4 DRAM design, where everything is within the DRAM die, right? We have all the processors within the die. We have all the banks in the die as usual. We have the control interface, and we have, of course, the unchanged DDR memory PHY. Then for the next generation, we are targeting a PIM-AI LLM chip or PIM-AI chip, which will be based on LPDDR DRAM design. In this case, we will have a stack solution where we will have the DRAM die with the DRAM banks, typical memory chip with unchanged LPDDR memory PHY, and we will have the local interface as well here in the DRAM die. And then on top of it, we will stack the logic die, where we will have a processor. Since we have more space, more area in the logic die, we will have a RISC-V processor with tensor units, vector units, so we have more compute performance, which is needed for AI applications. And we will have as well the control interface onto the logic die. As well, this is one chip of all for a product targeting mobile. But then we will be offering as well the PIM-AI DIMM, which is, as today, we will have 16 of these chips together, and they will incorporate a PIM chip interconnection that will allow chips to exchange data between other chips within the same DIMM. So let's first focus on the architecture of a single chip. So we have here on the left, we have the architecture of the chip. So we have the LPDDR5 interface and the local interface in the DRAM die, as said. And in the logic die, we will have the DMA communication with the banks, and we will have a shared memory or L2 cache. And we will have 4 cores with their L1 cache, the vector unit, the tensor unit. This design will allow us to get more than 100 gigabytes per second in a chip of 2 gigabytes of DRAM. And since we are not going through the memory controller, we are behind the memory controller, we have a much better energy efficiency. We have less than 1 picojoule per bit when accessing the memory, meaning that we have much better performance because of the compute that the RISC-V processor will allow us, because of the much better energy efficiency, meaning that we'll have as well a better total cost ownership. This chip will be a set 2 gigabytes with 5 teraflops of floating point 16 capabilities, but we will support as well other data types, such as FP8 or INT8, INT4. Again, it can be associated with other chips, maybe not at the D level, but within a SoC, maybe we can put together 2 or 4 chips, so we can increase the compute capabilities and the memory bandwidth, the overall memory bandwidth. Again, this architecture requires no changes in the SoCs, which is really good for future SoCs that they are aiming to compute AI applications. So this makes actually we think that the ABUMPIMP PIM makes the enabler of the generative AI, mostly LLMs, on smartphones. For cloud, as said, we will put together 16 of these chips in a DIMM with the chip interconnect. So this will allow to exchange data between chips within the same DIMM. This is really useful because, for instance, if you want to parallelize an algorithm, mostly AI in this case, you want to have the same input for all the chips, so you can parallelize actually the compute operations. So in this case, when we apply tensor parallelism into a model, into an LLM model, what we will do, we will write the whole input, the initial input, which probably will be the prompt for the model. We will put it into the DIMM, and internally the chips will exchange its part of the input with the neighbors. This means that, of course, if you want to synchronize between chips within the same die, you don't need to go to host. So you save some transactions on there. Of course, as today, if you want to synchronize between DIMMs, you will have to go through host, through the DDR interface. So let's go for the evaluation of this architecture. We develop, we benchmark different large language models. And so first, we have a small recap on what is a LLM model. So mostly LLM is quite similar to this scheme, let's say. You will have sequential layers that are to be executed. These layers can be matrix operation, matrix multiplications. You can have activations. You can have different concatenations, for instance. You can have different layers, but mostly the most intensive ones in the models are usually the matrix multiplications, which we can see in this plot, right? And then the execution usually consists in two steps, if we assume that we have a key value cache. The first time that we execute the model, it's called encoding, that is executed the first time. So the first time that we execute the model, we will fill the key cache. And the input for this phase is the whole prompt or the words or the tokens that the user wants to inference and generate new tokens. So in this case, since we have a matrix as input, every time that we go to a layer and we have to load the weights in order to do the matrix multiplication, we will have a lot of data reuse for these weights, meaning that the memory bandwidth is not the bottleneck in here, but the compute performance, because we have to actually compute a lot of rows for the operation. Once the encoding phase has finished, we go to the decoding phase. The encoding phase will generate a new token, and this will be the new input for the decoding phase, which is executed several times. Every time that we want to generate a new token, we have to execute the decoding phase one time more. In this case, the input is usually a single row, meaning that when we load the weights and we want to do this matrix vector multiplication, the memory bandwidth in this case will be the bottleneck, and compute performance is not that important in this case. So for the evaluation, we developed a LLM simulator, a high-level simulator with a standard PyTorch running on x86. It can run any LLM model or almost any neural network that it's developed in PyTorch. We actually, the numbers that I will show you now in the following slides are sourced from Hugging Face without any modification. And the simulator is able to get an accelerator profile which describes the hardware that the model is execute. With some key, this accelerator profile has some key parameters for instance, the bandwidth, the compute capabilities, or the energy that it takes to generate a result. And at the end of the execution of the model, the simulator will output a lot of different metrics. I will be showing you mostly Llama and Mistral models running in multiple targets, right? We have the UPMEM PIM chips. We have different SoCs from Apple, MediaTek, and Qualcomm. And I will show you a use case also for cloud, which will be comparing against an NVIDIA server. And it will be showing you encoding and decoding information and the overall performance as well. Have in mind that we can put the length of the inference and the number of generated tokens that we want and the quantization that we want, but I will show you sub cases of all the benchmarks that we have done because of time constraints, right? Also to mention that all this simulator has been developed with real information on different high-end RISC-V multi-core IPs with vector units. We know the time that we will take to execute different matrix multiplication, matrix vector multiplication, activations, etc. So the simulator is quite straightforward, meaning that if we see here on the right, we have top to bottom execution on the model. We start with the input, which usually is the prompt of the user, and we will finish with the inference, the new generated tokens. And we will be executing different layers. So we capture the start and the end of this execution, and a profiler is attached to this execution, and we can get real metrics from the hardware that is running in. And as well, we have a simulator that will simulate the execution in a given hardware profile that we set. Of course, we have to pass some information on the layer, and at the end of when we get the output of the inference, we will get as well some summary of the simulation. So let's go for the evaluation. We will start with the mobile models and SOCs. So here we have the description, the accelerator descriptions that we fed into the simulator. So we have 3 different system on chips. We have the Apple one, Qualcomm, and MediaTek latest SoCs. Also, we have the ABUMPIMP PIM chip, only one single chip. And just for reference, we have the Samsung PIM approach. But I won't be showing you results on this because they have a different approach on what PIM is supposed to look like. But we'll comment on the numbers now. So one of the differences is that when we go, the communication between host and the device, or in case of the SoCs is the NPU, the neural processing unit, they have the same bandwidth for host-device communication, host-to-device and device-to-host, because they are accessing all memory chips at the same time, so they can get the full bandwidth. While for PIM chips, you cannot get that because you are accessing only a single chip at a time in order to get data, to write data. So we have less bandwidth here. But then we go to when the accelerator is accessing actually the memory to get the weights. We see that we have, for the SoCs, they have the same bandwidth because they are accessing the same memory. But for PIM, we see that we have better bandwidth, and actually we have a much better energy efficiency. We have less than 1 picojoule for Samsung and for ABUMPIMP. And then in terms of compute, we see that the teraflops that Apple and Qualcomm and other companies are around 5 teraflops, which is something that ABUMPIMP can achieve. And in the Samsung one, because they have a different approach, they have a really low number of teraflops. So let's go with some benchmarks. Yeah. So I'm showing you here the Llama 2 7B and Mistral 7B with these data types for all the weights and the activations, everything. We assume a batch size of 1 because we think that in a mobile, the user is a single user that will be doing requests to the model. And we are simulating or generating an input of 1,000 tokens in and 100 new tokens out. And we can see on the left plots, we have the encoding phase, and we see that mostly with the ABUMPIMP PIM it takes the same time to achieve the first token, meaning that to execute the encoding phase, than the other SoCs. But we have a better energy efficiency, a bit more energy efficiency, because at the end, remember that in this phase, teraflops are the most important ones and not memory. The most interesting for PIM is the coding phase, where we see that we can achieve better tokens per second, meaning we can execute more times the model than the other SoCs, because we have better memory bandwidth. And as well, we have a much better energy efficiency because of this processing in memory that we can get. If we get everything, if we sum the encoding and the decoding phases, we see that we can achieve up to 45% more queries per second than other SoCs. And in terms of energy, we can be up to 13 times better in terms of energy per query. Of course, in a mobile environment, maybe the queries per second is not that significant because you are one user that is requesting an execution of the model, and you don't mind if it goes a bit faster, a bit slower. But what you really mind, I think, is that you can do more inferences with the same battery, right? So if we have an average battery, PIM can achieve 10 times more requests on this average battery. So for Cloud Accelerator, we will be comparing against the DGX H100, which is 8100 GPUs. And it has a factor size of 8 Us. And it has almost 650 gigabytes of HBM. We have a PIM server, which is similar to what we have today, which is 24 PIM DIMMs, and each DIMM, again, 16 PIM chips with 8 teraflops interconnected in the same DIMM, and almost 800 gigabytes of PIM chips. So to be fair, we will be comparing one DGX H100 server and 4 PMI servers because they have the same rack occupancy. And you can see here the differences in the accelerator profiles that we fed to the simulator. So first, for the NVIDIA solution, we have the host-to-device and device-to-host bandwidth. And we see that we have quite a lot of bandwidth because we assume that all data can be kept in the GPUs. So we model 8 NVIDIA switches. So every time that they need to synchronize, they don't need to go to host, but they can go through the different switches. For the PMI server, of course, we have host-to-device is only 22 gigabytes per second because we have to write one DIMM at a time. And we cannot parallelize that, and it takes what it takes. When we go in the opposite path, the device to host, we have the aggregated bandwidth because we can read from all the DIMMs at the same time, mostly. And then in terms of main memory, the NVIDIA has almost around 25 terabytes per second for the HBM, while ABUMPIMP server can achieve almost 40 terabytes per second with a much better energy efficiency, right? Of course, if we go to the compute capabilities, the NVIDIA solution has more than twice teraflops than the ABUMPIMP PMI server, and we will see how this translates into the plots. So in this case, we have the Llama 2 70B, which is more convenient for cloud, and we have the Mistral 822B. We have these data types for quantization, and we have the batch size depends on what we are running, right? What we are running and where we are running. Because we have a limited memory, we assume that we want to fill all the device with all the possible batches. And I'm showing you the GQA and multi-head attention, the group query attention and multi-head attention. Mainly the difference between these approaches is that the GQA requires less memory per batch, and it's less demanding in terms of memory bandwidth because it groups different batches in order to generate the KB cache and to store it. But the bad effect on this is that the model accuracy can be degraded. So I'm showing you both approaches. Of course, the MHA approach will fit less batches since we need more memory to store all the batches. So if we have a look at the encoding phase, we see in the first token latency, the execution of the first encoding phase, we see that the PMI servers are worse because they have less teraflops. Remember that it's less important, the memory bandwidth here, but the teraflops is what matters. Anyway, we have a better energy efficiency here. And you can see also in the encoding phase that you can see that the performance when we are using multi-head attention drops because we are accessing more data in memory. And the difference between PMI servers and DGX H100 servers is less, which is the same for the decoding. In the decoding phase, it's where PMI shines, right? So we are able to generate more tokens per second, so we can execute more times the model per second. And then, in terms of energy, we see again a bit of difference between the GQA and multi-head attention. Again, since we are accessing more data in the MHA, we get more benefits from PIM. If we go on to the overall performance, we see that we can get up to 61%, I think it was, 61% more queries per second in GQA, and while we have a similar energy efficiency. Yes, and so overall, the total cost ownership is much better for PMI. So for conclusions, I'll show you that for the next generation of PMI, for PIM, we will be introducing the PMI chip with RISC-V ISA with AI capabilities seamlessly integrated into DDR5 and DDR5 memory chips. Again, same as the current generation, no memory controller changes, no memory PHY changes. We will have up to 8 teraflops, and again, we will have less than 1 picojoule per bit when accessing main memory. And in the hardware evaluation with the simulator, we showed that the total cost of ownership per query per second in a cloud scenario can be improved almost up to 7 times. And in a mobile scenario, we can generate almost 50 more better tokens per second, while improving the energy efficiency from 10 to 20 times. The idea is to open source this LLM simulator that we have been working on, so everyone can check the different performance on different devices. And we are developing a QEMU and Gen5 simulator, so customers or potential customers can assess the performance on this approach, on this architecture. Okay, so that's all for me. So